What's going on, everyone? Welcome back. Patrick here, and moving on with two-sample hypothesis testing, we're now going to talk about the F-tests for variances over the next couple of videos. And before I get into the specifics of that, I want to go over a summary of what we've covered so far in this section. So if you remember from the overview video, we had this diagram over here. We had two-sample hypothesis testing, and it was split up into two cases initially. We had independent samples. We also had dependent samples, but we haven't gone over the dependent samples case yet. So I'm going to leave that out, just focus on this part of the diagram. So two independent samples, and then you could further split that up into two cases, whether you know the population standard deviations. If you do, you use a z-test. If you don't, further split it up into two cases. Either the two population standard deviations are assumed to be equal, then you do a pooled variance t-test, and if they're assumed to be not equal, you do a non-pooled variance t-test. And we did examples for all of these cases here. Now, one thing I want to mention is you'll see in questions, sometimes they'll say the population standard deviations are assumed to be equal, or the population variances are assumed to be equal. And they both basically mean the same thing. So the variances you would show like this. It's basically that standard deviation squared, right? But both of these are the same thing. You could either square both sides here to get to here, or you could square root both sides to get to there, right? And same thing here. Population variances are unequal, right? So whether they tell you the population standard deviations are assumed to be equal or the population variances are assumed to be equal, they both mean the same thing. So in that overview video, I mentioned how there's a test to see whether the population standard deviations are going to be equal or unequal. Notice that in the questions before, when we did a pooled variance t-test and a non-pooled one, we were told in the question, assume the variances are equal or unequal, but what if we don't know what to assume? We got to run some kind of test for it. So you can actually put another level here. You can do an F-test. And then that F-test is going to tell you whether those population variances or standard deviations are equal or unequal. And the process, the general process, is going to be exactly the same. So you're going to have some kind of population. Let's call it population 1. You're going to have population 2. And both of these populations are going to have some kind of standard deviation or some kind of variance. Let's just work with variance, right? So sigma of population 1 squared, that's the variance. Sigma of population 2 squared. The problem is that lots of times these populations are big. So let's say like this is like 10 million people, this is 10 million people. It's going to take a lot of resources to go and figure out what that actual population variance is for both populations. So what we do, as we've been doing, is we take a sample from each. So this would be sample 1, and then this would be sample 2. And what we do is we take a certain amount, right? We sample a certain amount of items from both populations, and we figure out what their sample variances would be. So this would be like S1 squared or S2 squared. S1 by itself would be the sample standard deviation. So S1 squared would be the sample variance. Same thing here. S2, sample standard deviation of this population. S2 squared would be the sample variance. And then what we want to do is we want to test if there's any differences between these. And then from there, we can see how much evidence we have to make a conclusion about these actual population variances and their respective differences or non-differences. So how are we actually going to go about this process if we start getting a little bit more technical? Well, it's actually going to be the exact same process as we've been doing with just hypothesis testing in general. So what we're going to have to do is we're going to have to state a null and a alternative hypothesis. We're going to have to find critical values. The difference is that when we're doing an F-test, these critical values are going to be on something called an F distribution. So far we've been just working with a Z distribution or a T distribution. We're now going to be working with something called an F distribution. I'm going to explain a little bit further soon what that is. So state the null alternative, critical values, and then we're going to have to find some kind of test statistic. See where it falls in relation to the critical values, and then we're going to know, are we going to reject the null or are we going to fail to reject the null? Now at this step, number one, when we're stating the null and the alternative hypothesis, you can have different formats like before. You could have a two-tailed test. You can also have one-tailed test, which would be split up into a left or right-tailed test. So let's start off with an example of a two-tailed test. I feel like that example is going to encompass the most, and then you could just apply all of that to a one-tailed test if you ever run into it. So the null is going to be that the population variances are assumed to be equal. And so the alternative would be that they are not equal. Right? So exactly like we had with the means, there's pretty much no difference. And because there's an equal and non-equal sign here, we know that this is a two-tailed test. Right? So if the alternative hypothesis had a greater than sign over here, then we'd be working with a right-tailed test, and then this would be less than or equal to. And if this was a less than sign in the alternative hypothesis, we'd be working with a left-tailed test. So then the null would have a greater than or equal to sign. So the formats are pretty much the same. It's just instead of the means, you're now subbing in for, instead of the means, you're going to be putting in the population variances. And then once you have your null and your alternative, now we got to get the critical values. And here is where we're going to introduce a new distribution. So what I'm actually going to do is I'm going to relate it first to the normal distribution. So the normal distribution, we know it looks like this, and it goes from negative infinity to positive infinity. And it's perfectly symmetrical, and we got that 0 in the middle here. Well, an F distribution, it's a little different. The way it looks is it's going to look like this. Right? So it's a little skewed to the right. Sometimes you'll see the F distribution being described as being skewed to the right, meaning that more of the data is on the left side. It's a little bit counterintuitive. You'd think that if it's skewed to the right, more data would be on the right, but if something is skewed to the right, it means that there's more data on the left side. And it doesn't go from negative infinity to positive infinity. It actually starts at 0. So what I'm going to do now is I'm going to erase this normal so we're not getting confused. Right? So notice that the F distribution, it's not perfectly symmetrical. Right? Because there's like this more data here on the left than on the right. So it starts at 0 and then it goes to positive infinity. Right? So there's not going to be any negative F scores, quote unquote, if you want to look at it like that. Versus with the Z distribution, with the T distribution, we were able to have negative Z scores or negative T scores. So that's how the F distribution looks. And if we're doing a two-tailed test, let's say that our significance level is 5%. Right? So when we're doing an F test, you're still going to be given a significance level or a confidence coefficient. So they could say with 95% confidence, then you know the significance is 5%. So because we're going to be doing a two-tailed test, exact same thing is going to happen. We're going to have a critical value here and then a critical value here. You know what? I'm actually going to make this closer to the axis like that. Right, so because this is a two-tailed test, there's two critical values like we had before. If it was a one-tailed test, we'd only have one critical value, either on the left side or the right side. So if the significance level is 5%, same thing, that 5% is basically split up evenly between these two areas. These are going to be the rejection regions. So this is going to be 2.5%, and then this here is going to be 2.5% as well. Question is, how do we find these two critical values over here? Well, we can do it in two ways, like before. We can use something called an F table, right? And that's for the F distribution, or we can also use the stats calculator. I'm going to show you both ways. First thing I want to point out is that when you're dealing with an F distribution, because it deals with two samples, it's basically going to be the ratio of the two samples. There's actually going to be 2 degrees of freedom. So T distribution, there was 1 degree of freedom. With an F distribution, there's going to be 2 degrees of freedom. And what you're going to see is that they're split up as one of them being with the numerator and the other being with the denominator. And I'm going to explain in a little bit why that numerator and denominator is there. It basically has to do with the format of the test statistic. But for now, what I want you to know is that the degrees of freedom of the numerator depends on the first sample. And it's actually equal to that first sample size minus 1. Right? And then the degrees of freedom of the denominator is going to be based on that second sample size. So it's actually going to be n2 minus 1. So let's do an example. Let's say that we took 2 samples. The first sample size was 16, and let's say the second sample size was 12. Well, plugging that into here, we know that the degrees of freedom of the F distribution we're going to be looking at for these 2 samples, the degrees of freedom, I'm going to put an n here for numerator, it's going to be 16 minus 1, which would be 15. And then the degrees of freedom for the denominator is going to be 12 minus 1, which would be 11. And there's actually going to be multiple F distribution, obviously because of the different degrees of freedom, but also depending on this upper region over here, right? So when you look at F tables, you're going to see multiple F tables based on this upper region. Some are going to have an upper region of 10%, some are going to have an upper region of 5%, 2.5% like we're working in this case, even 1% or even 0.5%. So what you want to do is you want to look for the table that has that upper region of 2.5%. So we're going to be using that specific table. And then what you're going to see in the table is there's going to be certain columns, there's going to be certain rows. And the rows here are basically related to the degrees of freedom of the denominator. Right? While up here, it's going to be the degrees of freedom of the numerator. And so what you want to look for in the table is the 11th row, because that's the degrees of freedom of the denominator, and then the 15th column, because that is the degrees of freedom of the numerator. And you basically look for that value that connects those two. And the value in the table, as you'll see, is 3.3299. Right? Make sure you're looking at the right table, that upper area of 2.5%. And so that is going to be this value over here. So that's going to be that upper critical value. Right? Sometimes you'll see this shown as like FU, right? The F value, the upper critical value. And you can also get this value with the calculator if you want to. So you would go to stat, you would hit F5 for distribution, F4 for the F distribution, and then F3 we're going to find the inverse of F. We're going to be finding the F score, quote unquote. So then you get to this input screen here. Data is variable. Now this area here, similar to the t-distribution, it's always talking about the right-tailed area. So with a z-distribution, you could specify whether you're looking at the left, the right, or the center. With the t-distribution, you can't specify. It's always going to give you that, you always have to input that right-tailed area. Same thing with the f-distribution. So if we're looking for this number here, that right-tailed area is 2.5%, so you put 0.025. And then notice we have 2 degrees of freedom inputs. So with the n here, that's going to be for the numerator. So that's going to be 15. And then this is going to be for 11. And then when you execute that, you should get that same value of 3.3299. Right? So that's how you get that upper critical value, whether through the table or through the calculator. Now, this lower critical value, with the calculator, it's pretty simple because notice that if we're here, if this area is 2.5%, then what's this entire area over here? What's that entire right-tailed area? If we're just looking at this, so ignore that upper critical value. This entire area is going to be 97.5% if this is 2.5%. So to find this, you could just plug in. The only thing you could change here is this area would be 0.975. And when you execute that, you'd end up getting 0.3325 if you round it to 4 decimal places. And so that would be that lower critical value. So you can easily get it with the calculator. Now, getting this lower critical value with the table, it's a little bit more weird. It's more complex. I'm still going to go over it because your prof may mention it. Basically, to get this, let me erase this here. Here's how I like to think about it. To get that lower critical value, it's basically going to be 1 over the upper critical value when the degrees of freedom are swapped. All right, so a little bit weird, but what you want to find is the upper critical value if the degrees of freedom are swapped. So instead of the numerator, degrees of freedom of the numerator being 15, the denominator being 11, you want to swap them. So you want to find that upper critical value when the degrees of freedom of the numerator would be 11 and the degrees of freedom of the denominator would be 15, and still with that upper region of 2.5%. So you're going to get a different upper critical value here. It's not going to be this one. It's going to be different. And then when you get that upper critical value, what you do is you take 1 and divide it by that. And that will give you the lower critical value for this distribution. All right, so hopefully you got all that. As I said, it's a little bit weird, a lot easier to just get it with your calculator, but if you do have to get it with your table, that's how you have to do it. You have to find the upper critical value when the degrees of freedom are swapped, and then take 1 and divide it by that upper critical value to give you this value over here. And when you look up that upper critical value with the degrees of freedom of the numerator being 11, degrees of freedom of the denominator being 15, you would get this value, 3.007827772. You could also get it with the calculator. So you get that, and then you take that number, or you take 1 and divide it by that number. So 1 divided by 3.007827772. And that would give you this number, 0.3325. Right, so if you got to get that lower value with the table, it is a little bit more annoying. My suggestion is to just get it with the calculator if you are allowed to use calculators in your course, or if your specific prof is allowing it. And then the final step is to just find the test statistic, right? Step 3. And luckily, with an F test, the test statistic is super simple. So the F test statistic. The formula is basically the sample variance from sample 1 over the sample variance from sample 2. That's pretty much it, right? So we don't have to work with this complex formula like we did with the other two-sample hypothesis testing that we've been doing up to this point. So let's pretend that, let's say this sample 1 variance, we got like 20, and this was like 8, right? So the test statistic would be 20 divided by 8, which would give us 2.5. Right, so that would be the F test statistic. And where does that 2.5 fit on this diagram? It fits about, let's say, right here. And actually, something I forgot to mention, these two regions, just like before, these two regions is where we're going to reject that null hypothesis. And then this region over here is where we're going to accept that null hypothesis. So if we are rejecting the null hypothesis in this case, then what we're saying is there's more evidence pointing towards the alternative, meaning that there is evidence that there's differences between the two population variances. But if we continue to accept the null or fail to reject it, then there's not enough evidence of differences, so we continue to assume that the population variances are equal. And notice that because this test statistic fell in that acceptance region, not enough evidence of differences between those two population variances, right? So we continue to assume that they are equal, right? So pretty simple. Couple of points I want to make for finishing off the video. Usually, you want to try to set up your two samples where the higher sample variance is going to be sample 1. Because what that's going to allow you to do is it's going to allow you to get a number here that's going to be greater than 1. And then you only have to really compare that test statistic to that upper critical value. Because this lower critical value, it's always going to be less than 1, right? It's always going to be less than 1 because it's going to be like 1 divided by a whole number. I guess it depends on the significance level, but usually it's going to, most cases, the majority of cases, going to be less than 1. But if you set up your test statistic where you're making sure that it's greater than 1, then really all you have to do is compare that value to that upper critical value and see is it less than or greater than, and that will tell you whether to reject or fail to reject the null. But it doesn't really matter as long as you have both of these. It doesn't really matter what way you structure the samples. I'm just saying, usually me personally, I like to structure it in a way where that higher variance is going to be in the numerator. One more thing I want to mention is this was a 2-tailed test, but what if we had a 1-tailed test? So let me erase this here. Like, what if we had a right-tailed test where we're checking whether that population variance from population 1 is greater than population 2, if that's the alternative hypothesis right there? Well, there would only be one critical value, right? So it would be over here. And if we're still working with a significance level of 5%, we're not splitting it up between two regions. This whole region here would be 5%, right? Same thing if we were working with a left-tail test, right? Then there would be one critical value on this side, and that whole region would be 5% as well. So you'd be looking at different tables and plugging in different areas in the calculator to find those critical values. But yeah, that's pretty much the process. I'm going to do a couple of examples in the future videos. So same thing, you're just finding the critical values, finding the test statistic with that super simple formula, and then seeing where does that test statistic fall in relation to the critical values.